All right, just give me 1 second. Okay, let's jump into the next question. So that's question 6 for today's session. 4.9 kg ball is dropped from a height 10 meters above one end of a uniform bar that pivots at its center. Okay, so let's draw this question as we go along. So there is a bar, and we have a 4.9 kg ball which is dropped. Okay, the bar has a mass of 5.5 kgs and is 7.8 meters in length. If the other end of the bar sits another 5.3 kg balls unattached to the bar, the dropped ball sticks to the bar after collision. How high will the other ball go after the collision? Okay, so we have another ball here which is unattached but sits on the bar, and the first ball is dropped. So this height is given to be 10 meters, and this thing is pivoted about the center. So when this ball gets dropped and it sticks, essentially what happens is the bar rotates and moves downwards, and this end would move up, and this would launch the ball upwards in air. And the overall length is 7.8 meters. So firstly, what we can do is, we know that initially this ball had some potential energy, but it did not have any kinetic energy since it was dropped from, it was dropped. So it was not thrown, it was dropped. So when it hits the bar here, all of its potential energy would be converted into kinetic energy. So therefore we can say that mgh, or let's call it m1, m1 and m2. Okay, so m1gh is equals to half m1 v square, which is the potential energy equal to kinetic energy. So the masses get cancelled out, and we get v is equals to square root of 2 times gh, which is equals to 2 times 9.8 times the height, which is 10, which is equals to times 10, 14. So we get the velocity to be 14 meters per second. This velocity is the velocity with which mass 1 hits the bar. Now we need to translate this velocity and find the velocity for bar 2. That would be the initial velocity with which it's launched up. So to do that, we need to think of the principle of conservation of linear momentum, of angular momentum. So when this block falls here, this falls down with an angular momentum, and when this block is launched up, that goes up and has an angular momentum associated to it as well. So what we can say is that the angular momentum of block 1 would be, or the angular momentum on this bar due to block 1 is equal to angular momentum which this bar would give to block 2. And the equation for angular momentum is given by m1 v1 r is equals to m2 v2 r. R in both the cases are the same because they are both the same distance away from the pivot, so they cancel out. Therefore, we can actually solve for v2 from here. So we will get v2 is equals to m1 over m2 times v1, okay, which is equal to 4.9 over 5.5 times 14.
Okay, so this becomes equal to 4.9 times 14 divided by 5.5. 12.47, which is the velocity of the second block. It's important to note that we were able to use this conservation principle because it says that the first block, when it fell down, it got stuck to the bar. Otherwise, we won't have been able to use the principle. Okay, now with that in mind, and we have the initial velocity of block 2, what we can say is when it goes up, all of its kinetic energy would be converted to potential energy. So what we use for block 1, we're reversing that and saying, oh hey, initially this block has some kinetic energy, but when it goes up, it would all be converted into potential energy. So we can say that for block 2, Ke is equals to potential energy. So kinetic energy is equal to potential energy by the law of conservation of energy. So we can say that half m2 v2 square is equals to m2 gh. The masses get cancelled out, and we're left with h is equals to v2 square over 2g, which is equals to 12.47 squared divided by 2 times 9.8. Okay, squared divided by 2 times 9.8, which is 7.3. Okay, now it's very important to note that this actually makes sense. The reason I say that is if you have a lighter block which is dropped on here and a heavier block is on the other side, and this is dropped from 10 meters in height, the heavier block would actually not go up as much as 10 meters. It would go up a few less smaller distance. So it did go a smaller distance up, which is 7.93 meters. Okay, so let's look at the solution. We solve for v, which is initial v, which is 14. The angular momentums are the same. We calculate v2, which is 12.9. Fairly, maybe I miscalculated it. 4.9 times 14 divided by 5.3. I see. So they actually used. Okay. So this should have been 5.3 because the bar was 5.5 kgs, but the block was actually only 5.3 kgs. So this is 5.3, which makes it 12.9. Okay, so this is indeed 12.9 meters per second. And then for block 2, everything is correct, just we have to replace this quantity to be 12.9 squared. So this is 12.9 squared, and we get the final answer as 12.9 squared divided by 2 times 9.8, which is equal to 8.49. So it went up a bit higher than what we had originally estimated, but as you can see, it still went lesser distance than the initial 10 meters. Okay, so the answer is correct indeed in this case. Okay, well.